Okay, so this is a different kind of factoring. These are special forms. And the special forms all have to do with perfect squares. So let's just get warmed up by expanding each of these expressions. What do we mean by expand the expression? FOIL, exactly. So you're going to FOIL them. Okay, so let's FOIL them together. 5x squared, or no, 5x times 5x is the same thing as 25x squared. Good. 5x times 3 is plus 15x. Good. Negative 3 times 5x would be negative 15x. And then last, negative 9. Good, or minus 9. Now, can you simplify that? Once you FOIL it, can you simplify it? What would simplify? What are our like terms? Oh, so what happens to these middle terms, the oi? Yeah, they're exactly the same number with opposite signs. So our simplified answer is 25x squared minus 9. And that's fully expanded because we FOILed it, we multiplied it. Okay, so what we call this example is the difference of two squares or dots. And this is the algebraic form, okay? If you have the exact same binomial with opposite signs, it multiplies to a perfect square minus a perfect square. So hence dots. Don't you love that? Some of my students came up with that. I made them do a lot of dots, so they had to get an acronym for it. So what was I going to say about that? Difference of two squares, dots. Oh, in order to factor these, we're going to always want to look for perfect squares. What are perfect squares? 1 times 1 is 1. 2 squared is 4. 3 squared is 4 squared. 5 squared. 6 squared. 7 squared. 8 squared, 9 squared, 10 squared, 11 squared, 12 squared, okay? That's 13 squared, that's 14 squared, that's 15 squared, that's 16 squared. I think 278, I better stop there. 278, I think, is 17 squared. I don't know. Anyway, you don't have to memorize all those. You pretty much know up to 144. But if you know your times tables and you know your perfect squares by heart, it just makes identifying these special forms that much easier. So if you look at a times table chart, you're going to notice right down the diagonal of the times table chart are what? Perfect squares. That's because 12 times 12, 11 times 11, 10 times 10, okay? So memorizing the perfect squares just makes it easier to identify this special form. If you look at example 2, x minus 6 or x squared minus 16, a difference of two squares is always a what kind of polynomial? Binomial. Yes. So this is a binomial. Why is this a binomial? Exactly. So how would we factor it? Well, we know that x times x gives us x squared minus 4 plus 4. Does everybody see that pattern of being able to factor? Those are the only two numbers that are going to multiply together to give us negative 16, but add to 0. B, by the way, is equal to 0 because 0 times x equals 0, right? So that middle term, the oi term, is 0. If we were factoring it the traditional way, we would say we're looking for a number that multiplies to negative 16 but adds to 0. Do you see why it would be 0 in the middle? And so they have to be the exact same number with opposite signs. That's the only way you're going to get 0, aren't you? Okay, so let's just try another one. X squared minus 25. What would that one be? X minus 5. You see how these are supposed to be a lot easier. What if you had 16x squared minus 49 y squared? Oh my gosh, can we do that one? How would we factor that? 4x, because 4x times 4x would give you the 16x squared, right? 4 times 4. Minus 7y plus 7y. Do you see that? Factoring? Any questions about how she got that? How many people are on board with this? Yes? Yes? Ask the question. Oh, you're on board. Good, good. I thought there was a question. Okay, are you ready for the next one? This is difference of two squares. Yes, ask it. Yes. So really what we're doing is we're taking the square root, right? The square root of 16 is 4 because 4 times 4 gives you 16, right? And x times x gives you x squared. Here it's going to be y times y gives you the y squared, and 7 times 7 gives you the 49. The fact that they're exactly the same with opposite signs means that if I were to FOIL and get the outside inside, I would have 28xy minus 28xy, which is the reason why the middle term is 0. You see that? So you're really looking for perfect squares here. Now there's another example we're going to get to right here about perfect squares. So how would we expand this? By the way, a lot of people will erroneously say 49, let me try again. They will erroneously, meaning it's not correct, if you say 49x squared plus 4. This actually doesn't exist, okay? Well, it doesn't exist in our world. We cannot factor it. What happens when you see this square, it really means 7x plus 2 times itself. And when you multiply a binomial times itself, you always have to FOIL. Okay, let's FOIL this. What's that going to be? 49x squared outside, 14x, good, inside, 14x, last, plus 4, okay? All right, how would that simplify now? Yeah, you have 2 of these, right? 49x squared plus 28x plus 4. So anytime you square a binomial, let's write this down. Anytime you square a binomial, you get a PST. A PST are these two. So this is dots. And these bottom ones are called PST. Do you want to know what that stands for? Perfect square trinomial for the win. Yes, perfect square trinomial. Okay? So if it's a perfect square trinomial, that's really awesome because, again, it gives me clues about how to factor it, okay? So I see 49, that's a perfect square. I see x squared, that's a perfect square. I see 4, that counts as a perfect square. So when I go to this example below, 4y squared is a perfect square, correct? 25 is a perfect square, correct? Now, don't worry about the middle term just yet. What would you have to multiply together to give you 4y squared? What number times itself? 2y times 2y, correct? What would you have to multiply together to give you a 25? 5 and 5. And because these are both positive, right? They're both positive. What's the sign? What are the signs going to look like? Positive, positive. And what you'll notice if we already know that the first and the last are going to work. Let's check the OI, the middle, right? Let's just check the middle. Outside, what's outside going to be if we multiply? 10y. What's the inside going to be? 10y. What do those add together to? 20y. So I'm just checking the middle because I already know that the first number is a perfect square. So yes, that will work, right? I already know that the last number is a perfect square. So yes, that will work. So I'm just checking the middle to make sure it's a perfect square trinomial. Because it's possible that it might not be. You could just, you could do the AC method here as well, but wouldn't it be easier just to go with that perfect square trinomial? So if we look at these formulas back up top, the difference of two squares is saying a squared minus b squared is going to always factor into a, which was a times a, okay, minus b, meaning the square root. Essentially, a is equal to the square root of a squared, right? B is equal to the square root of b squared. So that's where we're getting those a's and b's from. If you look at the trinomial, it's saying that if I FOIL a binomial, if I square a binomial and I FOIL it, it's always going to be a squared. So we're going to square the first number, square the second number, and then have 2 of a times b. That's the outside inside. We have 2 of the outside inside. So that's where that 2ab comes from in that formula. Now you notice with the perfect square trinomial, it always has to end in a positive. Why is the last term of a PST, a perfect square trinomial, why do you think it's always positive, the last term? Any ideas? Well, let me give you another example and then we'll come back to that question. So what about this one? Let's say I had 36x squared and my last term was 49. I'm using 49 quite a bit, okay? And this is negative and this is positive. Don't worry just yet about what the middle term is, because I'm not exactly sure. No, I'm just kidding. Okay, if you ignore the middle term, how would that factor using a PST? So 6x, 7, right? 6x, 7. Talk to me about the signs. What would the signs have to be? Both negative, right? Both negative. Because the whole point about a PST is it's a perfect square. It's basically this, isn't it? Now let's check and see what would be this middle term. Does anybody know what the middle term would have had to be for this to work out? It would be, what's outside? Yeah, negative 42x. 42x. What's inside? Negative 42x. If we add those together, what do we get? Negative 84x would have been that middle term, right? So when you see perfect squares, it's an invitation that it should hopefully be a little bit easier. But again, that comes back to memorizing our perfect squares so we can identify them right away. That's going to be so useful moving forward in math, knowing the perfect squares by heart, okay? Let's look on the next page so we can see a couple more examples. One thing I need you to realize is that this form, I think there was a warning. Wasn't there a warning? No, it's not on this one. Okay, here's a warning for you. Those are two special forms, but the warning is a squared plus b squared is prime. Okay? And that's because you don't distribute the square over a binomial. All right? If you look at this one, you probably want to try and factor it. But remember, I always said check to see if it works. So a lot of people think that this factors into x plus 2 squared. Do you see that? A lot of people will try to factor it like that. But let's prove that that doesn't work by FOIL. X plus 2, so we're going to FOIL it, times x plus 2 would be what? Plus 4x plus 4. Oh. But if you did x plus 2 times x minus 2, what would you get if you FOILed that? You'd have x squared minus 4. So this one, guys, is prime. Okay? This is the same example as that. We don't have sum of two squares. There's no SOTs. There's only dots, difference of two squares. The fact that you have the difference here, so right here, the two things that we FOILed is this one is PST, right here, perfect square trinomial. This one is dots, difference of two squares. Okay? Let's look on the page and let's see if there's one we can identify here. Oh, I know. Here's a couple of examples. Let's do this one together. Okay? Q to the fourth minus 81. Is Q to the fourth a perfect square? Yeah, because Q squared gives us Q to the fourth, right? So Q squared times Q squared would give us Q to the fourth. Talk to me about the signs. Talk to me about the last number of each binomial. Positive and negative. I hear the signs. And what number? 9. Great. Okay, now here's the other thing about factoring. You don't stop until you can't factor anymore. Is any one of these factorable? Which one? This one is the sum of two squares, the one we were just talking about. This one is prime. Because we just proved that we cannot. If you want to keep trying to factor it, I encourage you to try. I'm going to tell you right now, it's not going to factor. Okay, if you don't believe me, try it. Please, I invite you to. Prove me wrong. Okay, what about this one right here? Difference, you're always looking for subtract. This is a difference of how many squares? 2. Difference of two squares. So this one's prime, it can't factor. So the prime one, we just leave it alone. Can anyone tell me how you would factor that difference of two squares, the Q squared minus 9? Q plus 3, Q minus 3. Does everybody see that that one factored down more? Okay, so this is fun. Let's keep going. Number one rule of factoring. Always look for a, let's write that down. Number one rule of factoring is look for a GCF. Now, I don't just mean look for it. Oh, took for? How can I spell? Rule of factoring is to look. Sorry about that. Look for a GCF. Typo. Now, if you find one, factor it out. Do you see an E? Do you see one? A GCF? 2. They're both even, so they're both divisible by 2. So we're going to divide by 2, factoring out the GCF. And that becomes minus 25. Can that be factored further? What's that one called? Does it have a name? What's it called? It's called a difference of two squares. This one, right? Difference, subtract. Square 1, square 2. So now the GCF is going to come down in front. Who can tell me what the factor pairs are? T to the fourth, because t to the fourth times t to the fourth, or t to the fourth squared is t to the eighth, right? Talk to me about the signs. Opposite signs for a negative, negative, positive. What should the last number be? 5. Now 5 is prime, so 5 is not a perfect square. If that number in orange had been a perfect square, this would also be a difference of two squares. But it's not, because 5 is not a perfect square. 5 is a prime number, okay? Let's look here at F. Remember what we said? Whenever it starts with a negative, here's another rule about factoring. If it starts with negative, factor out the negative. So I see the negative in front here. Is there a bigger GCF just besides negative? Five is not a perfect square for this one. Yes, yes. So 25 is a perfect square, but I meant like, okay, for instance, that's a really good question. Okay, I'm going to write it down here. I meant if it had been like t to the fourth minus 9 example. That's a good example. So 9 is a perfect square, right? That means that this t to the fourth minus 3, t squared minus 3, t squared plus 3. I'm saying if the 5 had been a perfect square, this could have been factored further, right? Because we determined in the last example that anything to the fourth power is also a perfect square. But it can't be factored any further. It's done. But I just meant if the second number had been a perfect square. Okay, so now let's go back to over here. It starts with a perfect square. What are you going to factor out? What's the GCF? Okay, so GCF is negative 16. So I'm going to divide out a negative 16. Even though those are perfect squares, still, they both are divisible. And what do you get then? T squared minus 4. Okay, so that was the first step, was the GCF. Now what? Can it be factored any further? Yes. What would you factor it to? T minus 2, T plus 2, right? Perfect squares. Looking for perfect squares, okay? There's no more squares. 2 is not a perfect square, T is not a perfect square, so it can't be factored further. Okay, let's look at some of these ones. Now again, if I look up front and I say, oh, that's a perfect square, and then I get excited because I'm like, 9 is a perfect square, maybe it will work. What would you start by factoring it? Please don't use the AC method here because you will be hurting. It's too big of a number. Don't use the AC method if they're perfect squares. Try to see if it's a perfect square trinomial, right? It's a trinomial with 3 terms, and 64 is a perfect square, isn't it? So what times what gives you 64y squared? 8y times 8y. And what times what gives you 9? 3 and 3. Look at the signs here. Here's a negative, here's a positive. So they're both negatives. Let's check the middle term. Check to make sure you get check OI. Does everybody know what I mean by check OI? Outside, inside. That's negative 24y. What's the inside? What do these add up to? Oh, and that's the middle number right there. You see, I'm just checking the middle. I already know the first and the last are going to work. Yes? Not all the numbers. The middle number is not a perfect square. just the first and the last. And so this is why I'm saying, like, when you notice the perfect squares, get excited about it and just see if it will work. It might not. You might have to use the AC method if it's not a perfect square trinomial. And by the way, any perfect square trinomial is always going to factor to a binomial, squared, right? A perfect square trinomial. That's where the idea of the perfect square comes from, is because you're squaring a binomial. Okay, I'm going to give you a little moment to practice before we come back and do some more.